If I ask you in elementary school what makes a graph or a curve continuous, the elementary definition is I don't have to lift up my crayon when I'm drawing that curve, right? When we're doing the AP test, however, you can't say, oh, that graph is continuous or not continuous because I didn't have to lift up my crayon when I drew that graph, right? There's something called a formal definition of continuity, and we have to know these three reasons what makes something continuous. And then if I ask you why is it not continuous, it has to be based on one of these three reasons right there. These three things must all be true for something to be continuous. If just one of these three items fell, the graph is not continuous. So this is the technical notation and language, all right, that we're gonna have, but I'm gonna walk through real quick and just translate that into normal terms for us. So to make this graph is continuous everywhere, okay? So we could just say this is continuous from negative infinity to a positive infinity. So if a graph is continuous, you don't need to do anything else for that. If it's not continuous, we're gonna go into detail what I want you to do for that, okay? So to make a graph continuous everywhere, it says f of c is defined. That just means it has a y value. So to have a graph there, I mean, you have to have a y value there, right? You have to have a point there. And this says the limit as x approaches c of f of x. So as you go along that graph, the limit as x approaches a point, like to the left and to the right of it, is a finite number. So what that means is, one, we have a limit. So the limit actually exists and is finite. Finite means it's a finite number. It's not infinity or negative infinity. So it's a finite number there. And then the third stipulation, which really the whole entire thing, the nuts and the bolts, is for it to be continuous, the limit has to equal that y value. This is notation for the y value. This is the limit from the left and the right-hand side. So to be continuous, the limit has to equal the y value. So what I want to do here, I have 4 graphs, and I just want to go through each one of these stipulations and just put a check if it satisfies that, or put an X if it doesn't satisfy that. And then if I ask you why a graph is not continuous, we'll go through and make sure we're clear out the 3 reasons that you're going to use right there, okay? So first of all, if I said, okay, number 1, does it have a y value? Everywhere, all right? So I'm just talking about at point C. So at point C, if I said, does it have a y value? You should hopefully tell me, yes, it does have a y value. There's a closed dot right there. So yes, that first one is satisfied. This one says the limit as x approaches C is a finite number. So the limit exists and it's finite. So remember from our very first video lesson here, limits graphical approach, if you do the limit as x approaches C, remember when you do your stick figure value and you travel along the curve from the left-hand side and the right-hand side, that limit does exist. The y values are always approaching whatever this y value is over here. The y values are getting closer and closer in conversion upon that picnic table. So that limit does exist. But then the third stipulation, so the limit answer is down here. See how the y value is up here where you got the closed dot. So the third stipulation is not true. The limit is not equal to the y value. So if I ask you, why is that graph not continuous using the formal definition of continuity, what you can put there, you could put this exact notation, limit as x approaches c of f of x is not equal to f of c, or you could just put simply in simple terms is that the limit is not equal to the y value. And you just need to give me that one reason why that graph is not continuous. You could also have written it like this. You could put limit as x approaches c of f of x is not equal to f of c. Or if I had a 2 right there, then you could change the c's to 2's there, but the limit is not equal to the y value. Going to the next graph, if I say, okay, at x equals c, do we have a y value? No, there's a vertical asymptote right there. There is no y value. So if I say, why is this graph not continuous? You can just put, there's no y value at that x equals c. That's your reason, okay? You can't tell me because there's a jump in the graph. You can't tell me because there's a vertical asymptote in the graph. Those are nice reasons in your head. Those are the flags that tell us that graph is not continuous because we know we had to lift up the pen when I drew that, but you have to use the formal definition of continuity. So don't tell me because there's a jump or a hole. Don't tell me because there's an asymptote. you got to use our 3 reasons, and we'll recap those after we do these problems. Now, once you tell me one reason, then you ain't got to worry about anything else. As one of them fails, the graph is not continuous. So just for purposes of being thorough, I am going to kind of go through these other ones. The second stipulation says the limit is a finite number. So if I ask you, does this limit exist? Hopefully you're shaking your head. Yes, a limit does exist because the left-hand side and the right-hand side are both going up to a positive infinity, but it says the limit has to be a finite number, because when you're going to infinity, you're going to have that vertical asymptote right there, and it's not going to be a continuous graph. So the second stipulation is also not true, that limit is not a finite number. So an additional reason that you could have given me, you just got to give me one. But if you didn't give me this reason, you could have written down the limit. You could have written down the limit is equal to infinity, or you could have written down the limit is not a finite number, because that is going with your formal definition of continuity. Now, if you don't have a y value, and then it doesn't really make sense to ask ourselves the limit is not equal to the y value. So you couldn't really use that as your reason right there. All right, and then the last graph, this is like piecewise function. We got this step function. I'm going to talk about at each integer. So like at right here, this would be like C1, this could be C2, this could be C3. And if I say, okay, at C1, do I have a y value? I do. It's right there. That's where I got the closed out. It's not down there, but it is down there. So I do have a y value. At C1, is a limit a finite number? Well, at C1, if I do a limit as x approaches C1, from the left-hand side, you're on this step. From the right-hand side, you're on this step. So that limit does not exist. So if you have a y value, but you don't have a limit, that third thing doesn't make any sense to talk about, whether the limit is equal to the y value right there. So your reason on this one is why this graph is not continuous is the limit does not exist. If the limit doesn't exist, then you're not going to have a continuous graph right there, because your limit must exist and be a finite number. That's one of the 3 stipulations for that to be continuous there. Now remember, anytime the limit doesn't exist, you have to tell me why the left-handed limit is not equal to the right-handed limit right there. So this is the reason that it's not continuous. This is the reason that the limit doesn't exist. Sometimes people just write down left-hand limit is not equal to the right-handed limit. And you're just giving me the reason why the limit doesn't exist. You got to write down the limit doesn't exist first, because that's the reason why this graph is not continuous. And then this left hand not equal to the right hand is the reason why that limit does not exist. So let's recap here. If I were to give you a few graphs like this on a testing situation, and I say use a formal definition of continuity, tell me why a graph is not continuous. These are the 3 reasons that you would give me, and we have them all right here. You could say simply no y value. You could also say the limit doesn't exist and then tell me why, or the limit is not equal to, the limit is not a finite number. All right, and then we saw no y value, the limit is infinity, the limit doesn't exist, and then you tell me why. And then the third reason is you could just write down the limit is not equal to the y value. Now, there's not really, when you're doing your homework, it doesn't really mention the formal definition of continuity, but it's really important for the AP test. It disappeared for a while from the AP test, and then it came back in a major way. So we have to learn it, get exposed to it, and then when we review, I'll have a study guide for you that will refresh our memory on. But these are the 3 reasons, okay? I don't want to have anyone taking a test and then say, oh, because there's a jump, or because there's an asymptote, because there's a hole in the graph. Those aren't valid reasons if they say use a formal definition of continuity. So it's got to be one of these 3 guys right here. What I would like for you to do, since the book doesn't do a great job of this, what I would like you to do, I believe on the first 3 homework problems that you got to do, they give you a few graphs and discuss the continuity. I want you to use this formal definition on those first 3 homework problems there. And then just tell me if it's continuous, just say it's continuous. You ain't got to do nothing else. But if it's not continuous, say, hey, it's not continuous at x equals 2 or x equals 3. And then tell me why using one of these 3 reasons that we talked about right there. All right, and then almost done here. This next thing in this section is actually really, really simple. We're going to give you some functions, And we're going to say, hey, classify, once it's not continuous, it's discontinuous, we want to classify these discontinuities as a removable kind or non-removable kind. So a removable discontinuity is just like if you have a line or a curve with a hole in it. That's a removable kind, graphically speaking. A non-removable kind is if you have a jump in your graph. So if you have a piecewise function and it just kind of goes like that and there's like a jump in the graph, or if you have a vertical asymptote, those are the non-removable discontinuities. So if there's just a single point missing a hole in the graph, that's removable. If you have a jump, if you have a vertical asymptote, non-removable. That's if you're looking at the graph. If you're looking at the function, I don't think we really want to graph these functions right there, okay? So you could tell algebraically what makes it removable or non-removable, okay? If it cancels out, if you could factor and cancel it out, then it's a removable kind, because when you're canceling, it's like you're removing that problem area. If it doesn't cancel at all, then it's a non-removable discontinuity, right? So what we can do here, here's an example, all right? We know we can factor this. We can make this x plus 2, x minus 2 over x minus 2. Now, if I say where is it not continuous, first thing you got to do is always take the original denominator, set that equal to 0. So if I take that original denominator, set that equal to 0, what this is giving me, I know that this means it's discontinuous at x equals 2. So that is your point of discontinuity. That's where your bottom of that fraction is equal to 0. So it's discontinuous at x equals 2. And now what we want to do is classify that as removable or non-removable. And here's how you can tell. See how these x minus 2's cancel, and you're just left with the x plus 2. So if it cancels out like that, that's what makes it removable. And then from your pre-cal days, the graph of this function right here is identical to the graph of y equals x plus 2, except there's a hole at x equals 2, all right? And then when we cancel it out, so that's why the limits, when you do the limit and go to the left and to the right of that, that's why those limit techniques work there, okay? So if you could factor and cancel it, that's the removable kind. Right here, if I say, where is this not continuous, you could say this is discontinuous. You always set the original denominator equal to 0. So that's discontinuous at x equals 1. And if I ask you to classify that now as removable or non-removable, it doesn't cancel out. There's nothing I can do to get that x minus 1 to cancel out, which means it's non-removable. And then remember when we graph things like that in our pre-cal days, that was like a vertical asymptote right there, that you graph those things, you would say, hey, x equals 1 is a vertical asymptote, and then you also get like y equals 1 is a horizontal asymptote, and then you just do the graph of the hyperbola branches right there. Let's do one final example. First thing I could do is just factor these things, right? So we can go x plus 5, x plus 3. We can go x minus 4, x plus 1. No, I'm stupid. X minus 4, x plus 3 right there. All right, now, if I say where is it not continuous, that's where the original denominator is equal to 0. So a very common mistake is students cancel this and get the simplified version of x plus 5 over x minus 4 and just say it's only discontinuous at x equals 4. That is incorrect, all right? Very common mistake. You always got to take the original denominator, set that equal to 0 to find your discontinuities. And so when I take this original denominator, set that equal to 0, that's telling me it's discontinuous at x equals 4 and x equals negative 3. All right, now, typically, just to help you out here, sometimes when I give a test, I might give you a function like this. I might ask, where is it continuous? And then I have you classify it as removable or non-removable kind. So if it's not continuous at x equals 4, negative 3, that means it is continuous everywhere else. So if we use our interval notation like we're supposed to be using, you're going to go from negative infinity to negative 3, skip over that, go from negative 3 to 4, skip over that, go from 4 to infinity. That's where the graph is continuous because it's discontinuous at those two numbers. And then removable, non-removable. So notice that these x plus 3's cancel out. So that's the removable kind. We just put down x equals negative 3. The x equals 4, the x minus 4 doesn't cancel out. That's the non-removable kind. That's the x equals 4. So if I graph this function, I would have a vertical asymptote at x equals 4. That's the non-removable kind. And then at -3, whatever that graph is doing, I'm not doing the exact graph here, but whatever at x equals -3 is, let's say the graph is kind of going up like this. At -3, there's going to be a hole in the graph. That's what makes it the removable kind right there. And you can't tell that, you know, we will eventually start working with the graphing calculators, but you're not going to be able to tell that there's a hole in the graph there unless you kind of look at the algebra going from there.